Thank you. Yes, I'm doing my PhD in Louvain under the supervision of Dr. Louvain, and I'm very glad that I have the opportunity to speak here today. So the goal of the talk is to examine properties of the functor category A to T, where A is the quasi-abelian category and T is the finite category. And we do so by making use of the full subcategory F of A to the T, which we define in the following way. So given a repeat full subcategory S of T, we define the object of F to be the functors from T to A, which map any object which is not in T to 0. And then the two main results are that an extension alpha from alpha G, where alpha F in A to the T is central with respect to F if and only if alpha T is an answer for all T nevertheless. And secondly, an n-fold extension A in A to the T central with respect to F if and only if alpha 0 T up to alpha n minus 1t are generally for all t. So if you don't understand a word that I just used, no problem, I will explain them and following. But this is the goal of the talk. Okay, I want to start with the following overview. So in the late 1980s, George and Nietzsche developed categorical grammar theory as a generalization of classical grammar theory, and a particular instance thereof is given by the categorical theory of central extensions, which itself generalizes the classical theory of central extensions to proofs. And Thomas Everhard, Louvain, and Thomas Linden developed then an axiomatic approach to the theory of high central extensions, which allows for a non-abelian approach to homology by a generalized subformula. And these indeed recover the Brown and subformula for integral homology of groups. So the key definition of categorical grammar theory is that of a Galois structure. I will explain that in more detail, but for the time being, I think of it as the data of a junction between two categories C and X, with left chain I and right chain H, and two classes of morphisms E and Z which satisfy certain conditions. And then the abelianization function from the category groups to the category of being groups gives rise to the Galois structure, which covers the theory of central extensions of groups. So in this talk, we will look at the Galois structure coming from the reflection of the functor category A to the T into F. Okay. So I structured my talk in three parts. First, I want to show you that F is a torsion-free subcategory of A to the T. This implies that F is admissible in the sense of categorical grammar theory, and that it's relevant to consider central extensions in A to the T with respect to that. And after that, I want to characterize the higher central extensions in A to the T. Okay, so let's start. As I said, the setup is that we have a quasi-abelian category A. I will recall the notion of quasi-abelian in a second. And a finite category T with a repeat full subcategory S of T. And as I said before, from these data, we construct the full subcategory F of A, T, whose objects are the functors that let any object from S to 0. So let us look at some examples. So in the following, I will give a natural number n as the set which contains all the natural numbers smaller than n. And then if we take as T, the opposite category of the partial order given by the power set of n, then A to the T is equivalent to the n-fold error category of A. And because we assume that A is quasi-abelian, this is also equivalent to the category of n-fold internal group points in A. So for n equals 1, the objects are just errors. For n equals 2, we have commutative groups. For n equals 3, commutative squares. And then for n equals 3, we have commutative cubes. And for S, we can, for example, take just 0, and then F is equivalent to A itself. And in the diagrams on the right-hand side, every point x not to 0 only but 1, which I cannot write. But we can also take F to be 0 up to n, and then F is equivalent to the n arrow category of A, by which I mean the category of complexes in A of length n. And again, because we assume A is quasi-abelian, this is equivalent to the category of internal n group points in A. So for n equals 1, the objects are given by errors. For n equals 2, we have two composable morphisms which compose the 0, and for n equals 3, we have three composable morphisms such that each composite of them is 0. Okay. Quick reminder of quasi-abelian categories. So the study of quasi-abelian categories goes back as far as Vanilla. Other names to mention are Poisson, Reinkoff, and then later Schneider and Hom. And you can think of quasi-abelian categories as nice regular additive categories. A precise definition can be given as following. So a category is called quasi-abelian if it is homological, so pointed, regular, and photomodular, and its opposite category is also homological. So examples of quasi-abelian categories are given by any abelian category, since we know that abelian means being exact and additive at the same time. But non-exact examples of quasi-abelian categories are, for example, given by the categories of torsion or torsion-free abelian groups, the categories of pathological or locally complex abelian groups, or the categories of pathological or normed binomial convex and pressure spaces. Okay, let me now show you that F is a torsion-free subcategory of A to the T, and I will start with F to show that F is normal epireflective in A to the T. For the proof, we first define for an object T in bold T in square brackets to be the finite set of morphisms which land in T and whose domain T hat does not lie in S. And then if we have a functor F from T to A, we take the co-product of all the images of the domains of all the morphisms T in square brackets, and I denote by Ft in square brackets with index T the induced morphism, which gives precomposed with the co-product inclusion corresponding to the morphism T star in square brackets of T F of T star. And then the image of an object T under the reflection IF of F is exactly the co-kernel of this morphism. And the morphism part of the co-kernel is the T component of the F component of the unit of the adjunction. Okay. Now let me show that F is also torsion-free, and the crucial property for this to be true is the following. So if we have a morphism F from A to B, then we can either first take its kernel and then its co-kernel, or first take its co-kernel and then its kernel, and this gives us an induced morphism between the image of F and the co-image of F. And in a quasi-abelian category, phi is always an epi. And now this, then one can define T to be the full subcategory of AT, whose objects are the functors such that this morphism T in square brackets I just defined is an epi for all T. And then one can show that PF is indeed a torsion theory in the functor category A to the T. Okay. In the following section, I will use this result. But before, let me recall some aspects of the categorical theory of sample extensions, which was developed by Nadja Egner and Compostela. And so this, imagine we have a category C and an object B in C, and we want to understand the category of extensions of B and C. So here E is a class of morphisms which we call extensions in C that satisfy certain properties, and we look at the full subcategory of the slice category over B whose objects are these extensions. And this is in general quite difficult to understand, but we can make use of a full subcategory of Cx, which we assume to be reflective with reflection I and inclusion H. And then if the data Cx, IH, and the class of extensions E and C, and a class of extensions Z and X assemble into a Galois structure, then this adjunction gives rise to an adjunction between the category of extensions of B and C and the category of Z extensions of the reflection I of B. And so here, what does it mean to be a Galois structure? So we have this adjunction, and furthermore, the classes of extensions E and Z must contain all isors, be closed under composition, and be pullback stable, and both I and H have to preserve the extension. Okay. Then, so here the left adjoint IB maps an extension of B just to the image under I, and here for the right adjoint HB, if we take an extension phi of I of B, HB maps it to the pullback of H phi along the B component of the unit of our original adjunction. And now one can ask the following question. As we assume that X is a full subcategory of C, can we also view the category of Z extensions of IB as a full subcategory of the category D extensions of B? And in general, this is not true, and hence leads to the following definition. So Galois structure gamma is called admissible if the right adjoint HB is fully faithful for any object B and C. So given such an admissible Galois structure, we define an extension F of B to be trivial if it lies in the essential image of this fully faithful functor HB. And we extend this class a bit by defining an extension to be central if there exists a monetic extension P such that the pullback P1 of F over P is a trivial extension. And here, an extension P is called monetic if the functor P star that maps an extension P to its pullback along P is monetic. And so here, this notion of central extension recovers exactly the notion of central extension of groups. Okay, so as I said before, we wanted to study the Galois structure arising from the reflection of AT in F. So the question is this admissible? And indeed, combining two results by Nadja Egner and Santiago and Louvain sees that any torsion-free subcategory in a homological category yields an admissible Galois structure where we can take the classes of extensions to be the regular Epis and C and X respectively. And as we've shown that F is indeed torsion-free and A to T, we get this Galois structure gamma to be admissible. Okay, in the following I will recall some general results and then apply them to this concrete example. And for this, gamma will be an admissible Galois structure where in addition C is a homological category, where the effective descent morphisms are exactly the regular Epis, and X is a regular epi-reflective subcategory C. And as classes of extensions, we take the regular Epis in both categories. Louvain and Galois show that in a quasi-abelian category, the effective descent morphisms are exactly the regular Epis, so our example meets all the conditions above. Okay, since F is a left adjoint between two additive categories, it is an additive function, and this will be the crucial property to be able to characterize the central extensions in AT with respect to F. And in fact, the extended notion of quasi-additive function is sufficient for that. And this notion was also introduced by Compostela and Louvain, and designs a functor between two functor categories A and B that preserves split short text sequences. So if we have a short text sequence KAB like this, then its image under I is the split short text sequence. And the crucial result is now that if we assume that I in gamma is further additive, then an extension is central if and only if its kernel lies in the subcategory X. For the proof, one can in general show that if F is a central extension, then its kernel must lie in X. But for the converse implication, the quadradditivity of I is essential. Okay, so let me show how one does this. So let us assume that we start with an extension F, whose kernel lies in X. We take its kernel pair and want to show that P1 is a trivial extension. Because we assume that in our category C, any regular epi is effective for descent, and the extensions are given by the regular epis, then this implies that F is central. So we want to show that the naturality square on the left-hand side is a pullback to show that P1 is trivial. But because we are in a homological setting, this is equivalent to the induced morphism between the kernel of P1 and the kernel of HI of P1 to be the isomorphism. And here we can use the quadradditivity because this implies that the kernel of HI of P1 is HI of the kernel of P1, and the morphism here is the kernel of P1 component of the unit of the adjunction. On the other hand, here the induced morphism between the kernel of P1 and the kernel of F is by construction an isomorphism. And now, because we assume that the kernel of F is an X, this implies that also the kernel of P1 is an X, but this exactly means that beta kernel of P1 is an iso, and this is what we wanted to show. Okay, so now we can apply this to our situation and get the following. So from extension alpha, from factor F to factor G, G, meaning that each component of alpha is a regular epimorphism. The following conditions are equivalent. Alpha is a sample extension, its kernel is an F, and alpha T is an ISO for all T that are not integers. So the equivalence of 1 and 2 is immediate, and also the equivalence of T and 3 is very easy to see, because kernel of alpha lies in F by definition, and kernel of alpha T is 0 for all T not in S. This means that kernel of the morphism alpha T is 0 for all T not in S, but because A was quasi-abelian, this means that alpha T is a mono, and also alpha T is by assumption a regular epi, so alpha T must be an iso. Okay, let me apply this result to two situations. So first, consider the adjunction between the error category of A and A itself. So given a morphism A from A1 to A0, F maps it to the co-kernel of A, and then U maps it to the morphism from 0 to the co-kernel. And given an extension F from an error A to an error B, this extension is central if and only if the component F1 is an iso. Secondly, let us consider the adjunction between the double error category of A and 2 error of A. So here, given such a square with vertices A11, A10, A01, and A00, F maps it to the morphism A upper index 1, followed by the composite of A lower index 0 with the co-kernel of A upper index 0. An extension between the square A, like here on the left hand side, and the square B is central if and only if this component F01 is an iso. And here, this shows that in a quasi-abelian setting, we found the characterization of the sample extensions between internal double profiles with coefficients in internal two profiles, for which we saw the reflection this morning in the regular master setting. Okay, let me now go to higher sample extensions. And for this, I want to start to motivate a bit why we study higher sample extensions. And as I said before, the adjunction between groups and abelian groups gives rise to an admissible Galois structure where the sample extensions are really the sample extensions of groups. And moreover, one can show that the category sample extensions is reflective in the category extensions. Namely, given an extension F from A to B, its universal sample extension associated to it is given by the induced morphism by the quotient of A by the commutator of the kernel of F and A. On the other hand, we know that if F is an additional representation of B, then the second top formula for the integral homology of groups is given by the quotient of the commutator of A with itself intersected with the kernel of F by the commutator of the kernel of F and A. So what we see here is that the same object, namely the commutator of the kernel of F and A, both appear in the centralization and the second top formula. And the question was then, can one define a notion of double sample extensions and then higher sample extensions, which relates to the Hop formula in the group case, and then Santiago showed this for double sample extensions, and as I said, Thomas Everhard and Mario Planet and Van der Linden did this for higher sample extensions, and then defined a suitable notion of homology using these sample extensions. Okay, and I also want to mention the work of Nadja Egner, who worked on beginning conditions where to study higher sample extensions. But so let me tell you, in the general setting, the idea is that one starts with a good Galois structure gamma, for which then the sample extensions are reflected in the extensions. And the goal is to define a good Galois structure gamma 1 to call double sample extensions the sample extensions with respect to gamma 1. And here the classes of double extensions, E1 and Z1, are still to be determined. But if this is achieved, one can repeat this procedure to obtain a good Galois structure gamma 2 and triple central extensions, and then so on. Okay, so I won't give you the precise definitions, conditions for a good Galois structure, but two examples. So the first one, gamma as before, where in addition I is still additive, so this applies to our situation. And another example I want to mention is where in addition we require C to be senior abelian and X to be Berkeley subcategory. Let me also give you the precise definition of the double extension. So given a morphism in the category extensions from an extension F to an extension F prime with components A and B, we call this a double extension if all the morphisms in this diagram are extensions. So in particular, we require the morphism A to the pullback of F prime to B to be an extension. And then this gives us indeed the class E1. Okay. And then one can really show that if one starts with a good Galois structure gamma, then one can construct in this way the extensions, the central extensions, the fraction inclusion, and then the double extensions, that this gives us indeed a good Galois structure, and then this gives us for any n larger than 1 a good Galois structure gamma. Okay. For the formulation of the following result, I will need the following notation. So if we have an n-fold extension A underlined, then we can see it as a functor from here up to C, which just means that for n equals 1, we view an extension as an arrow, double extension as a commutative square. And I will write AS for the image S of S for a subset S of n under A, and I will write AI for the image under A underlined of the inclusion of n without I into n, where I goes from 0 to n minus 1. So I can picture A as a bit diagram in C, where on the left hand side I have this object an, and n morphisms starting from there A0 up to an minus 1. And that I can formulate the following. So we also have a characterization of higher sample extensions if I is not additive, exactly by this condition that the intersection of all the kernels of these morphisms AI must be an X. And applied to our situation, this gives us that an n-fold extension A in A to the T is central if and only if here alpha I t up to alpha n minus 1 t are jointly monic for all objects T that are not in S. So here A is a functor, is a diagram of functors, and these alpha i's are really natural transformations. Okay, let me conclude by giving you the form of the general top formula in the proto-additive setting. And for this, I will write A in square brackets for the kernel of the A component of the unit. And then the result is that if P is an n-fold e-projective presentation of an object P, so P is an n-fold extension in particular, then this quotient where we have here the object Pn square brackets intersected with all the kernels of the morphisms Pi, quotiented by the square brackets of intersection of all the kernels. This object does not depend on the chosen presentation P and lies in the subcategory X. And then this is called the first general top formula and allows us to study homology in various situations. Okay. That's all I wanted to say. Here are my references, and thank you for your attention.
Other questions or comments? Please.
In the beginning, you assumed that category T is finite.
Yeah, so this was because I didn't, but I was interested in these n-error categories, and then everything is automatically finite because we have this finite set of morphisms into the domain. But if you, and also then you only need finite coproducts, so this was convenient. But you can also require any arbitrary coproducts and then do it for non-finite categories.
Other questions or comments? Okay, if not, let's thank Nadja.